Hello Year 11, welcome to revision week 17. In this video we are looking at Boolean logic, including logic gates, truth tables, and how to draw and write the expressions. And this is paper 2, topic 2.4. Make sure you've got revision sheet 17 ready to follow along and complete. Okay, firstly, before we start on the logic gates, remember, binary. Everything on the computer is done in binary, ones and zeros, base 2, but why and why is it used? Binary is used because computers are made up of millions of electronic switches or circuits. Each switch can either be open, closed, on or off, and this is recorded with 1 is on and 0 is off. 1 on, 0 off. And logic gates are basically the way of carrying out calculations and decisions based on these inputs and their Boolean outputs. Why, though, is binary used? Binary is high tolerance. That means it's less likely to make mistakes when you're telling the difference between 1 and 0 than you would be with a very accurate decimal number. For example, 4.26 and 4.27. It's much clearer. It's either one or the other. It's much clearer to record and use as well. It's either 0, 1, 0, 1, 1. And computers often only have two states they can use, on, off, north, south, in the way they are made. So 3 clear reasons there. So on your box, fill this in now please, this section of the sheet. Okay, checking your notes, Purple Pen's improving. So why is binary used? Because computer systems are made up of millions of switches. Each switch can be turned on or off. Binary value for 1 represents on and 0 represents off. And the advantages: binary is high tolerance, easy to record and use, and computer components often only have 2 states they can use. Okay, the logic gates that you need to know. And or not. So remember, logic gates are special circuits built into computer chips. They receive a binary input, a 1 or a 0, and they apply a Boolean operation, and or not for example, and then they output a binary result based on the inputs and the operation it does. Okay, it makes decisions based on the inputs and the operation that's being used, not, or, and for example. And the 3 main logic gates you need to know are and, or, and not. Look carefully at the shape: and with a straight back and curve like a capital D, or with a curved back and a bit more of a point to it, but like a shark's fin. And the not is a triangle with a little circle on it. Okay, triangle with a circle on it. Okay, so very simply, you should know this. An AND gate, it has 2 inputs and 1 output. And very simply, both of the inputs need to be on to create the output. If only one of the inputs is on, there's no output, and if none are on, no output. Both on produces an output. The OR gate, 2 inputs, 1 output. In an OR gate, only one or both of the inputs have to be on to make the output. However, if none of them are turned on, obviously, then there is no output. And finally, NOT gate. It simply reverses or inverts the signal. It's also known as the inverter. It does the opposite of the input value. So if it's off, it turns it on. If it's on, it turns it off. Reverses the input. Very simply, on this here, what is a logic gate? And draw the 3 gates and label them as well with the inputs and outputs. Okay, checking your answers. Definition: they are special circuits built into computer chips. They receive binary inputs, for example 1s and 0s, apply a Boolean operation, for example and or not, and output a binary result. And the 3 you need to know: and or not. Make sure you've labelled the inputs ABC, ABC, and just A and B on the not one. And make sure little things like you've got the little circle on the not gate as well. Okay, truth tables. So you've already seen these tables at the bottom here. That is a truth table. It shows all the possible outputs for a logic circuit or gate based on the different combinations of inputs. So whatever goes in produces an output basically. On the AND gate, remember, the output is off unless both of the inputs are on. On the OR gate, if one of the inputs are on or both of them, it produces the output, and the NOT gate inverts, it does the opposite. These truth tables show all the combinations for each of these logic gates. Notice when you're filling it in, very important, you're essentially counting in binary. So with two inputs, very simply, imagine these columns along the top, 1, 2. We are simply going to count 0, 0, 0, 1, which would be 1, 1, 0, which would be 2, and then 1, 1, which would be 3. So basically we've gone 0, 1, 2, 3. Now we've got the inputs done, we can then work at the outputs. So if both of them are off, in this case, C is our intermediary value here in the middle, that would be off. That would be off, that would be off. Only when both of them are on, it turns it on. And then P is the result of inverting whatever C is. It's our NOT gate. So if it's off, it turns it on, but if it's on, it turns it off. How about three inputs? Exactly the same. We count in binary, except we've got 3. 1, 2, 4. So 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1. And then we go to the next column. 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. And all we've done there is count in binary. 0, 1, 2, 3, 4, 5, 6, 7, etc. Okay? With our columns going up. Again, once we've gone that, we can then fill in our rest of our circuits here. So in this case, for D to be on, A and B have got to be on. And the only place where A and B is on are here on these last two values. And for X to be on, D and C both have to be on. And the only place where that is true is the very last one here, where C and D are both on. The rest, there are no two that are both on. Okay, on this section here, what was the purpose of the truth table again? And write out again the truth tables for the AND, OR and NOT gates that you need to know and recognise. Okay, checking your answers. What was the truth table? It shows all the possible outputs from a logic circuit based on the different combinations of inputs and outputs. And there's the three tables again, like we have seen. Checking your answers. Okay, as well as being able to recognise the gates, you have to be able to write and draw the circuits. This is easy, remember. All we have to do here is look at the outputs and inputs and write it as an expression, like in maths. So in this case, we always start with the outputs, in this case C. So we've got C equals A and gate B. A and B. How about this one? Well, the output is C, so we start off with C equals, and we've got A and a NOT sign gate, so it's not A. In this one, P is our output, and we've got A or B. P equals A or B. What about when we've got two different gates put together? Well, again, we always start at the end here. Output P. P equals. Now we've got A and B down here. However, everything goes through this NOT gate. The NOT gate is the last thing it goes through. So it needs to go around everything to show that everything goes through it. We put brackets around it to show it's gone through. How about a different way around? So here, again, look, we've got C as the output. This time, however, there's a NOT gate over here. So C equals, we've got not A here, A and a NOT gate, and B. The not A is in brackets, so however, because we do that first. Its ordering is done first. C equals not A and gate the input of B. And it also works the other way around here. C equals, we've got not A here at the present, at the start. We've got the OR gate, and then not B before at the start here in brackets. So either way. Okay, on your sheet, very quickly, write down the Boolean expression for these two logic circuits using our rule, always starting with the output at the end. Okay, checking your answers. We have Q equals A or B in brackets, because we do that first, it's before, and C, okay, because it goes through the AND gate. At the bottom, we've got Q equals, again, not A in brackets first, because it's done first, and B and C in brackets, because, again, that's done before. They both go into the AND gate here. And finally, last thing today, you have to be able to draw the gates. So very simple. What would the circuit look like for this? We've got our Z equals X or Y. So we've got Z at the end, remember, and we've got X or Y. Very simple. How about this one? D at the end is our output, and we've got not A and B. So remember, the not is going around everything, so it's going to go at the end, and we've got A and B here. So D equals A and B going through the not gate, is going around it. Here we've got E is our output, so that'll be over at the end on the right. We've got not A in brackets, so that's going to go on the left, and not B in brackets, that's going to go on the left. Not A and not B. And finally, X is our output over here. We've got A or B in brackets, because that's going to be done first. Big OR and the input of C. X equals A or B, or the input of C on its own. Okay, on your sheet, last task for today. Draw the diagram for these two expressions. Make sure you draw carefully the shapes of each of the logic gates and how they're connected together. Off you go. Okay, purple pen, check your answers. You should have Q as the output. We've got A or B in brackets, that's done first, and it goes through the NOT gate. Everything goes through the NOT gate. We've got E at the bottom here as the output, and we've got not A in brackets and not B in brackets, because that's done first. You don't need these intermediate stages of C and D in this example. Okay, as always, online community, revision quiz 17, check your understanding, check each question and try again if you don't get it right. 100% is your target. Good luck. See you in lesson.